Welcome. Today we will discuss the third scheme of speed control, that is sleep power recovery. So, first we will draw the equivalent circuit of the induction motor with a voltage source in the rotor circuit. V1 is the stator applied voltage, R1 is the stator resistance per phase, Jx1 is the stator leakage reactance per phase, E1 is the stator induced voltage per phase, and at a slip S the rotor induced EMF is SE2. E2 is the standstill EMF, and at slip S the induced EMF per phase is SE2. And because frequency of the slip rotor EMF is slip frequency, S times the fundamental frequency, the leakage reactance of the rotor is JSX2 and rotor resistance is R2 and rotor current is I2. And here we have additional one, that is a voltage source VR. So, VR phasor is the injected voltage, injected EMF in rotor per phase. So, you see for the voltage VR and I2 rotor current, they so give some power, and that power is PR. PR is the power absorbed by the voltage source in rotor circuit. So, mechanical power Pm equals to air gap power Pg minus power absorbed by the voltage source in rotor circuit PR, when rotor copper loss is neglected. So, you can see the magnitude and sign of PER plus or minus can be controlled by controlling magnitude and phase of VR. Okay. When PER is 0, PEM equals to PG, because you have neglected the rotor copper loss, otherwise PM is PG minus rotor copper loss. And in this case, motor runs on its natural speed, torque characteristic. A positive PR that is power absorbed by the source will reduce mechanical power PM and hence motor will run at lower speed for the same torque. When PR equals to PG, PM is 0, that is motor speed is 0, because mechanical power is 0, motor speed is 0. So, from this we conclude variation of PR, power absorbed by the source, from 0 to PG will allow speed control, from synchronous to 0 speed. When VR acts as a source, of power, PR is negative, and because PR is negative, mechanical power PM is greater than air gap power. So, motor speed will be more than synchronous speed. So, this corresponds to super synchronous motoring operation. Super synchronous motoring operation. This super synchronous motoring, this corresponds to equivalent to sub synchronous generating. Sub synchronous generating in doubly fed induction generator. So, in doubly fed induction generator, when the turbine speed is below the speed corresponding to synchronous speed, so generation is possible only when external voltage source in the rotor circuit injects power, adds power to the rotor circuit, generating power becomes possible. So, let us relate this technique to rotor resistance control. In rotor resistance control, slip power SPG, slip power is 3 I2 square R2 plus external resistance. So, by varying the external resistance, the slip S is varied. So, a part of the slip power is dissipated in the external resistance, and by varying this dissipation through external resistance control, slip is varied and hence speed is varied. But in this method of slip power recovery, slip power portion is usually employed in slip power recovery scheme while speed control is obtained. So, efficiency is better, efficiency of slip power recovery scheme is better and it is the maximum. So, there are two schemes of slip power recovery. First one is static Serbius drive, second one is the static Kramer drive. So, we will discuss static Serbius drive and static Kramer drive and how the slip power is used to control the speed of the induction motor. So, now we will discuss static Serbius drive. So, what are the features, salient features? The static Serbius drive provides the speed control of wound rotor induction motor below the synchronous speed. In this method, a portion of slip power from rotor is converted to DC by diode bridge rectifier. Then this rectified DC is converted to AC by line commutated inverter and then fed back to the AC supply through a transformer. Power fed back can be controlled by controlling the inverter firing angle. The DC link inductor is provided to reduce ripple in DC link current ID. Drive efficiency is high as the drive input power is the difference between the motor input power and the power feedback. Reactive power input is the sum of motor reactive power and inverter reactive power. So, drive power factor is poor. So, efficiency is better, whereas power factor is poor. These are 2 points. So, the scheme is like this. So, this is the 3-phase induction motor. So, 3 stator terminals are there, 4th terminal is just shown for from, and the rotor terminal, 4th terminal can be cancelled. So, there are 3 rotor terminals and 3 stator terminals. So, this is taken from a simulation diagram. So, the 3 rotor terminals are connected to a diode bridge rectifier, 3-phase diode bridge rectifier, and the rotor slip power is rectified, and then there is a filter LD. To the purpose of the filter is to reduce the ripple in the DC link current and also to avoid discontinuity of current. And then this rectified power is converted input to the inverter, line commutated inverter. So, phase control converter operating in inverting mode, firing angle above 90 degree, and this 3-phase line commutated inverter output is connected to a transformer, and then it is connected back to the supply. And here we have a starting resistance, because for to start at the starting the rotor slip is 1, there is a so there will be a problem for starting the motor will. So, for that starting the rotor must be connected through a resistance. So, starting torque is provided, and once the speed builds up, then line commutated converter can be used. This circuit configuration can be used. So, this is the DC link current ID, and please note that this is the VD1 polarity, and polarity of VD2 is shown, you mark it, that is important. It is normal polar, if the polarity according to this polarity of VD2 as we have written, we can write VD2 equals to minus 3 into root 6 phase voltage V by pi into, if the transformer ratio is M times cos alpha. Here this side is 1, this side is M turns. So, transformer turns ratio from the line side to the supply side to the inverter side is M is to 1. So, M turns in the supply side and 1 turn in the line side. So, voltage per phase voltage at the inverter terminal is V by M. So, 3 into root 6 by pi V by M into cos alpha, and minus sign is taken care. So, that VD2 polarity is as indicated. So, in different sources VD2 polarity can be opposite to this, and in that case minus sign will not be there. So, take care, and this is the slip power recovery scheme. So, let us assume V is the AC supply voltage per phase, N is the stator to rotor turns ratio of the induction motor. So, that rotor voltage at standstill condition is V by N, stator to rotor turns ratio is N. So, at standstill condition rotor voltage per phase voltage is V by M, at a slip S rotor voltage per phase is S V by N, and M is the transformer turns ratio from the supply side to the inverter side, alpha is the inverter firing delay angle, and VD1 is the DC output voltage of diode bridge rectifier, VD2 is the DC side voltage of the line commutated inverter, as we have marked here. S is the slip. With this you can write, you see rotor induced voltage per phase is S V by N, and 3 into root 6 by pi is the output voltage of the diode bridge rectifier VD1, and as I have already explained, the inverter output voltage, inverter DC side voltage VD2 is given by this expression, minus sign takes care of our polarity convention. Since voltage drop across DC link inductor is negligible, because DC link inductor it is basically filter with high inductance and negligible resistance, because so the resistance, if resistance is negligible, VD1 equals to VD2. Because we have taken the polarity of VD2 like this, then VD1 equal to VD2. If you take, if you ignore here minus sign here, you take VD2 of opposite polarity, then VD1 is minus of VD2. So, now because VD1 equal to VD2, equating these two, slip AC is given by minus n by m cos alpha. So, by varying inverter delay angle, firing delay angle, inverter terminal voltage VD2 is varied. Because VD2 is varied, power fed back, that is power fed back to the supply via the inverter is VD2 into DC link current ID. This is the power fed back. VD2 is the inverter output voltage and ID is the DC link current. So, by varying the firing delay angle alpha, VD2 is varied and slip power fed back to the AC supply is varied and speed control is obtained. Theoretical maximum value of the firing and delay angle is 180 degree, but it is restricted, alpha is restricted to a value less than or equal to 165 degree. That is for to have safe good commutation. At alpha equal to 180 degree, voltage value is 0. So, 0 voltage means no commutation failure may occur, line commutation failure can occur. So, to have good commutation, firing angle is 165, maximum firing angle is 165 degree. At start, alpha is maximum and at alpha equal to 90 degree, the speed is maximum, that is near synchronous speed, AC is 0. So, so by varying, alpha is controlled. By varying the alpha, speed is controlled. So, now we will see how to decide the transformer turns ratio. As you saw, the slip S in this static service drive is minus n by m cos alpha. So, and alpha maximum is 165 degree for commutation, good commutation, and by choice of m, required speed range can be obtained. Required speed range can be obtained by choosing the m. M is selected such that the lowest speed is obtained at the highest, at the maximum value of alpha. At the lowest speed, that is when S equals to S max, slip is the maximum value, VD1 is 3 into root 6 V by pi into S max by n, and VD2 is minus 3 into root 6 V by pi into 1 by m cos alpha maximum. So, as Vd1 equals to Vd2, this condition has to be satisfied. This leads to m equals to minus n by s max into cos alpha maximum. So if alpha max is 165 degree, this is minus n by s max, say cosine of 165 degree. Practical case we will take. So, this is 0.966 times n by s max. So, by choosing the transformer turns ratio by this expression, we can obtain the speed s max at 165 degree. So, such a choice of m ensures highest firing angle to be obtained at the lowest speed. Giving highest power factor. Next, for analysis purpose, we will draw the equivalent circuit of the motor. Refer to rotor. So, this is the rotor terminal. At the right side, we have the rotor terminal V2. V2 is the rotor EMF, and R2 is the rotor resistance per phase, and JSX2 is the rotor reactance per phase. And because we have taken the rotor EMF as it is at slip frequency, the reactance is JSX2, and at the input side voltage is S V1 by N, because V1 is the stator applied voltage, N is the stator to rotor turns ratio. Then at standstill condition, rotor voltage, starter voltage referred to the rotor is V1 by N. When the motor rotates with slip S, the EMF in the rotor circuit becomes S times. So, the stator EMF voltage, starter applied voltage referred to rotor becomes S V1 by N. And with this, the because the frequency is also slip times, the resistance of stator referred to the rotor is S R1 dash. R1 dash is the actual resistance of stator referred to the rotor, and S is because the current has to be maintained the same, and voltage has become multiplied with a factor S, current has to be maintained same. So, resistance has to be S times. Similarly, the slip is also S times. So, stator reactance referred to rotor is JSX1 dash, S because slip times. So, this is the stator equivalent circuit. Now, this equivalent circuit referred to stator, referred to the DC side, this equivalent circuit refer to the DC link side. We have the voltage VD1 and we have the voltage VD2 with polarity as shown. And the resistance is two SR1 dash plus R2 plus RD. Why? We are referring to the motor equivalent circuit from rotor side to the DC link side. So, to the DC link. So, DC link we have the rotor voltage V2 is referred is VD1 and inverter terminal side voltage is VD2 and they are connected by resistance, because in the DC link the reactances becomes 0, reactance have no role, and resistance when referred from the rotor side to the DC link side, resistances are multiplied with factor 2, doubled. Why? In previous class when we analyzed the slip ring in induction motor rotor resistance control, we see the external resistance from the DC side when referred to the rotor circuit becomes 0.5 times, that means half, that we have already derived. So, that means same resistance when referred from the rotor circuit to the DC side, it becomes doubled. So, total resistance in the rotor branch is R2 plus SR1 dash multiplied with factor 2 and DC link resistance of the filter is RD. So, this is the DC link equivalent circuit. So, from this DC link equivalent circuit, we can obtain the DC link current. So, DC link current ID, as you see from that equivalent circuit, it is VD1 minus VD2 divided by the total resistance is 2 SR1 dash plus R2 plus RD. Note that VD2 is minus of 3 into root 6 by pi V by m cos alpha. And with this DC link current, slip power is slip S times the air gap power. So, slip one part is dissipated in the rotor circuit rotor resistance as the rotor copper loss, that is 3 I2 square into R2 rotor copper loss, and remaining power is fed back to the supply, and power fed back to the supply is VD2 into ID, VD2 into ID. So, from this you can say air gap power PG equals to 1 by S 3 I2 square R2 plus VD2 into ID, air gap power, and the torque T is PG by omega S Newton meter. So, it is 1 by S omega S 3 I2 square R2 plus VD2 ID in Newton meter. So, if the speed torque graphs to be plotted, horizontal axis is the torque axis, vertical axis is the speed axis, this is the omega m at alpha equals to 90 degree. As alpha is increased to alpha 1, alpha 2. So, you have (90°) is less than alpha 1 is less than alpha 2 is less than 165°. So, as alpha is at alpha equal to 90°, we have the highest no load speed. At alpha equal to 90, we have the highest no load speed, which is close to the synchronous, very close to the synchronous speed. And as at the same alpha 90°, as the load torque is increased, speed reduces, given by the torque speed characteristics of the induction motor. And when the alpha is increased step by step, the no load speed obtained at 0 torque reduces, as shown by these points. This is the no load speed reduced, synchronous speed remains same, no load speed reduces, and as load is increased, the torque speed characteristic is followed. So, this is the set of torque speed characteristics for slip power recovery scheme. And we will draw a closed loop scheme. This is the 3-phase supply to the induction motor, and rotor terminals are connected to a diode bridge rectifier, and diode bridge rectifier is filtered by the filter LD, and in the rotor shaft there is a speed sensor. First, to give the speed feedback omega m, this is subtracted from the reference speed, command speed omega m star. Then the speed error goes through a speed controller. Speed controller output has to be the reference current, but again there should be a current limit control. This is the current limit control. So, output of this is the reference value of the DC link current ID star. Then actual DC link current is sensed and compared with the reference current, and DC link current error goes through a current controller. Current controller output is the control voltage Vc, which goes to the firing circuit of the inverter. This is the line commutator inverter whose alpha is controlled from the firing circuit in response to the control voltage V c, and this one is to M transformer, 3-phase transformer. This is the 3-phase line connected to the 3-phase supply. So, this is the closed loop control scheme. So, as indicated, speed controller output goes through a current limit control, which decides the maximum value of the DC link current, and that is also the reference DC link current, and actual DC link current is compared, and error goes to a current controller, which generates the reference voltage V c, control voltage V c, to control the alpha of the firing inverter in closed loop control. And the application of this closed loop speed control drive is in medium and high power drives. For high power means up to 10 megawatt. High power fan and pump drive. So, this is the application of static Servius drive. Then we will discuss the other one, the static Kramer drive. Static Kramer drive is a constant power drive. Static Servius drive is a constant torque drive, and this is a constant power drive, Kramer drive. So, this scheme is like this. So, this is the induction motor, 3-phase induction motor, and the output of the 3 rotor terminals of the slip ring induction motor are connected to a diode bridge rectifier, just like previous schemes, and then it is filtered. The rectifier is filtered through a filter inductor LD, and this is the input VD2 to a DC motor, the rectified output of the diode bridge rectifier is fed to a DC motor, and a DC motor is mechanically coupled to the induction motor. So, torque supplied to the load is sum of the torques produced by the DC motor and induction motor. So, total power remains constant, but in load speed can be controlled by controlling the field voltage of the DC motor. Through field control of DC motor, speed control is done, and torque supplied to the motor is sum of the motor torque and DC motor torque and induction motor torque. This is the static Kramer drive. Okay, thanks for attention.